Tonight we're diving into one of the biggest mysteries in modern science, the hidden 95% of the universe, dark matter and dark energy. If videos like this help you relax, think, or simply feel a bit more connected to the cosmos, please consider hitting like, subscribing and sharing this with a friend. Thank you for listening and supporting the channel. I would love to know what time of day are you watching, and from which place in the world are you tuning in. Tell me in the comments below. Matter in everyday experience seems solid, familiar and complete. Atoms build rocks and water and air, they build plants and animals, they build the planet and the star that warms it, and they shine across space as galaxies. For most of history, it appears natural to assume that this visible and tangible matter is the main substance of the universe. In the modern era of astronomy, this assumption quietly begins to fail. As telescopes grow more sensitive and detectors extend across many colours of light, astronomers learn how to count matter on a cosmic scale. They weigh galaxies by their motions, trace the glow left from the early universe, and track how elements are forged in the first minutes after the beginning of cosmic time. Independent methods converge on the same surprising conclusion. All ordinary matter, the kind that forms atoms and stars and planets, and living cells, amounts to only about 1/20th of the total cosmic content. The rest is dark. A larger share, roughly 1/4 of the total, behaves like matter in that it clumps under gravity and helps build structures, but it does not shine, absorb, or scatter light in any detectable way. An even larger share, around 2/3, does not behave like matter at all. It appears as a smooth energy associated with space itself, gently but persistently pushing the universe to expand faster. Together, these dark components make up about 19 out of every 20 parts of reality, leaving the familiar world of atoms as a small remainder. The numbers themselves are not arbitrary guesses. The afterglow of the hot early universe, known as the cosmic microwave background, carries a detailed pattern of tiny temperature variations. Sensitive spacecraft operated by agencies such as NASA and the European Space Agency scan this radiation across the whole sky. The sizes and strengths of the small patches on this sky map are influenced by how much ordinary matter, dark matter, and dark energy fill space. When researchers compare the observed pattern with theoretical models, only a narrow range of mixtures fits. That preferred mixture tells a consistent story in which ordinary matter holds a minor share. Another check comes from the light elements such as hydrogen, helium, and lithium that are created in the first minutes after the Big Bang. The relative amounts of these elements depend on how many protons and neutrons are present at that time, which in turn depends on the overall density of ordinary matter. Measurements of light element abundances in ancient stars match calculations that again point to a universe with only a small fraction of ordinary material. Galaxy surveys provide a third angle. With large telescopes on the ground and in orbit, astronomers map millions of galaxies over vast regions of space and reconstruct how structure grows over billions of years. In these simulations and observations, matter does not spread smoothly. It forms a pattern of dense filaments, clusters, and thin regions, a cosmic structure whose growth depends sensitively on the mixture of ingredients. Simulations that include only ordinary matter fail to reproduce the observed large-scale pattern. They produce too little clumping, and the timing of growth is off. When dark matter and dark energy are added with proportions similar to those hinted at by the early universe signals, the simulated universe looks much more like the real one. Each of these arguments arises from different observations, uses different methods, and relies on different sources of error. Yet they all point in the same direction: the visible cosmos is not the full cosmos. The familiar atoms that build human bodies and instruments and observatories are part of a minority component that floats in a much larger and more elusive environment. This realization changes the way the universe is described. Instead of a stage filled mostly with stars and gas, the universe becomes a system in which light-emitting matter rides in the gravitational field of an unseen medium and evolves within an even more mysterious expanding background. To keep track of this change, cosmologists adopt a simple inventory in which each component is assigned a density and a role in shaping the past and future of the universe. Ordinary matter interacts strongly with light and forms complex structures. Dark matter interacts mainly through gravity and provides additional mass to hold those structures together. Dark energy behaves like a property of empty space that influences the overall expansion. The fact that such a large fraction of the total substance of reality does not appear in any direct image creates a specific kind of puzzle. It is not merely that something is missing. The missing part is needed to make sense of structures that already exist and of signals that are already measured with high precision. Dark matter and dark energy are introduced not as decorative ideas, but as working explanations that make diverse data sets coherent. At the same time, they raise uncomfortable questions. If most of the content of the universe cannot be seen and does not fit neatly into known categories, how complete can present-day physics really be? The opening problem is therefore simple to state. Ordinary matter described by well-tested theories and directly observed in countless settings accounts for less than 1 part in 20 of the cosmic budget. The rest is assigned to dark matter and dark energy entities that are defined almost entirely by what they do, not by what they are. From this starting point, the story of modern cosmology becomes the story of how these invisible components are inferred, how their effects are traced, and how their unknown nature continues to shape every attempt to understand the universe as a whole. When astronomers look beyond the local neighborhood of stars and turn their instruments toward entire galaxies, they find that the quiet inventory of cosmic contents becomes a dynamic problem. A galaxy is not a fixed picture painted on the sky. It is a rotating system of hundreds of billions of stars, clouds of gas and dust, and invisible relics, such as stellar remnants, all orbiting around a common center of gravity. The way these stars move is not arbitrary. Their motions are governed by the mass of the galaxy. If there is more, mass gravity is stronger, and stars can orbit more quickly without flying away. If there is less, mass gravity is weaker, and stars at the outskirts of the galaxy should drift outward or never have formed stable orbits in the first place. By watching how fast stars and gas clouds circulate at different distances from the center, astronomers can weigh galaxies and see how their mass is distributed. In a simple picture that includes only visible matter, the expectation is clear. The inner regions of a galaxy, where most of the bright stars and dense gas reside, should dominate the gravitational pull. Outside this luminous core, the light becomes faint and the amount of ordinary matter quickly declines. Under these conditions, orbital speeds of stars should be high in the bright central regions and then decrease steadily with distance, much like the speed of planets falls off in a planetary system, where most of the mass is concentrated in the central star. For the outer parts of galaxies, the predicted motion is a gradual slowing, a gentle drop in rotation speed that mirrors the thinning of starlight. Actual observations do not follow this pattern. In the second half of the 20th century, astronomers such as Vera Rubin and Kent Ford used precise instruments to measure the rotation curves of spiral galaxies, which are plots of orbital speed against distance from the center. They expected to see a rise in speed near the center, followed by a decline in the outskirts. Instead, they saw speeds that rise and then level off, remaining almost constant far beyond the bright stellar disk. Gas clouds in the outer regions, where there is little visible light, circle the galaxy at speeds similar to those of stars much closer in. This behavior is not a small deviation that can be dismissed as measurement noise. It appears again and again in many galaxies across different environments and sizes. The implication is direct. If stars and gas are moving too quickly to be held by the gravity of the visible matter alone, there must be additional mass distributed through and around the galaxy. The amount of extra mass required is not minor. In many spiral galaxies, the unseen component outweighs the visible stars and gas by several times. The gravitational potential that shapes the orbit seems to come from an extended, roughly spherical halo of mass surrounding the luminous disk, a halo that emits no light and does not absorb or scatter radiation in a way that current instruments detect. This unknown component earns the name dark matter because it does not contribute to the galaxy's brightness, yet dominates its mass. Without it, the outer regions would not remain bound. The stars would slowly disperse into intergalactic space, and the spiral patterns seen in images would not persist over cosmic time. The same conclusion arises when entire clusters of galaxies are analysed. In these systems, dozens or hundreds of galaxies move within a common gravitational field, and their speeds can be measured through shifts in the light they emit. Decades before detailed rotation curves became common, Fritz Zwicky studied a cluster in the constellation Coma and noticed that its galaxies were moving so rapidly that they should escape the cluster's gravitational pull if only the visible matter were present. He inferred the existence of what he called missing mass. Later observations of many clusters using more accurate data and broader methods confirm his basic insight. The combined mass of the stars in the member galaxies and the hot gas that fills the space between them falls far short of what is needed to keep the cluster together. Once again, an unseen component must supply the extra gravity. Another way to weigh clusters uses the hot gas itself. This gas glows in X-rays and is confined by the cluster's gravity. Its temperature, density, and distribution can be measured by X-ray observatories. From these data, astronomers infer the depth of the gravitational well. The result nearly always points to the same imbalance. There is more gravity than can be explained by ordinary matter alone. The missing mass is not concentrated in compact objects such as black holes, because that would produce strong localized effects and likely visible signatures when matter falls onto them. Instead, the additional mass appears to be smoothly spread following the overall cluster structure. These converging lines of evidence transform the original suspicion about dark matter into a central feature of modern cosmology. Galaxies not made only of the stars and gas that appear in images. They are immersed in and largely shaped by a halo of dark matter that extends far beyond their visible edges. Clusters of galaxies in turn are enveloped in even larger dark matter structures. The bright parts of the universe, the regions that telescopes capture in photographs, sit within these invisible frameworks. The dynamics insist on it. Whenever gravity is strong enough to hold fast-moving material together on galactic and cluster scales, calculations using only visible matter fall short. The consistency of this pattern raises an important question. Is there truly an additional kind of matter, or is something wrong with the law of gravity itself when applied on very large scales? Some researchers explore modified theories of gravity in which the familiar rules change at low accelerations or over great distances, trying to reproduce the observed motions without invoking dark matter. In certain limited cases, these models can match individual rotation curves. But when a broad range of systems and other data are considered, they often struggle to provide a unified description. Dark matter treated as a new form of matter that interacts through gravity but not through light remains a simple way to explain the full set of observations in galaxies, clusters, and the growth of large-scale structure. Yet even as it succeeds as a framework, this solution is unsatisfying at a deeper level. The need for dark matter is inferred entirely from its gravitational effects. Its composition remains unknown. No direct detection in laboratories has yet confirmed what kind of particle field or more exotic entity it might be. The rotation of galaxies, the motions of clusters, and the survival of delicate structures over billions of years all point to the unseen mass, but they do not reveal its nature. The universe, therefore, appears stable and coherent only because it is filled with something that cannot yet be identified. Invisible matter shapes the architecture of galaxies and binds them into systems while staying outside the reach of direct observation. This situation, in which the fundamental mass component of the cosmos is known mainly through its effects, sets the stage for further inquiry. If dark matter is real and widespread, it must also influence phenomena beyond the motions of stars and galaxies. It should leave its mark on the earliest light in the universe, on the pattern of how structures form and merge, and even on the way light travels through space. Each of these arenas becomes a new testbed for the dark matter idea, and a potential source of fresh puzzles, as the universe continues to reveal that what holds it together is not what first meets the eye. On the larger scales, the universe does not appear as a random sprinkling of galaxies. When deep surveys map the positions of millions of galaxies over vast distances, a pattern emerges. Galaxies gather in filaments and sheets. They cluster at the intersections of these strands, and between them lie regions almost empty of bright matter. This arrangement is often described as a cosmic web, a kind of three-dimensional network extending for hundreds of millions of light years. The web is not fixed in time. It grows as small irregularities in the early universe gradually amplify under the pull of gravity. The nature of dark matter plays a central role in this growth. In the first few 100,000 years after the Big Bang, the universe is filled with a hot, dense mixture of radiation and matter. Tiny differences in density from place to place are imprinted in this medium. Light and ordinary matter interact strongly, so they move together, while dark matter, if it interacts only through gravity, begins to clump independently. When the universe cools enough for light to travel freely, and atoms to form the imprint of those early fluctuations is preserved in the cosmic microwave background sky, while dark matter has already started to fall into slightly denser regions. Over hundreds of millions of years, these small enhancements in density grow into the filaments and clusters seen today. Computer simulations are essential tools for exploring how this process unfolds. Researchers set up virtual universes with slightly uneven initial conditions, based on measurements of the cosmic microwave background, and then let the laws of gravity evolve these conditions forward in time. When the simulations include large amounts of dark matter behaving as a cold, slowly moving substance, the outcome is a network of structures whose size distribution and overall pattern closely resemble what galaxy surveys observe. Dense knots of dark matter form where many filaments intersect, and these knots provide the deep gravitational wells in which gas can cool, condense and form stars. In these models, ordinary matter largely follows the scaffolding laid down by dark matter. Where dark matter is dense, galaxies form. Where it is sparse, large voids emerge. The luminous structures are therefore traces of a more massive invisible framework. Without dark matter, simulations of structure formation fail in specific ways. If only ordinary matter were present, the radiation in the early universe would smooth out small fluctuations before they had a chance to grow, leaving too little contrast to form galaxies by the present time. Structures that do form would be different in scale and distribution from what is seen. When dark matter is included in sufficient amounts, it begins to clump earlier and more effectively than ordinary matter, preserving and amplifying the seeds of future structure. The agreement between these dark matter-based simulations and extensive galaxy surveys is one of the strongest arguments for the existence of a dominant unseen mass component. Observational evidence for this hidden scaffolding comes not only from the positions of galaxies, but also from the way they cluster statistically. By measuring how likely galaxies are to be found at various separations, astronomers build a quantitative picture of structure across different scales. These clustering measurements match the predictions of models in which dark matter forms the backbone of the cosmic web. The spacing between large clusters and the sizes of voids align with expectations from a universe dominated by cold, dark matter and dark energy. Another emerging tool is weak gravitational lensing, in which the shapes of distant galaxies are very slightly distorted as their light passes through foreground mass distributions. By studying these subtle shape changes across large areas of the sky, astronomers can reconstruct maps of the total mass, both luminous and dark. These maps reveal extended structures of mass that trace the same network suggested by galaxy positions, but add information where light is scarce. They show that most of the mass in large-scale structures resides in a component that does not shine. Dark matter halos overlap and blend into one another along the filaments, forming a continuous unseen skeleton that supports the visible universe. This picture leads to a shift in perspective. The stars and galaxies that capture attention in images are no longer the primary architects of cosmic structure. Instead, they are secondary features forming in the deeper potential wells carved out by dark matter. Ordinary matter cools, condenses, and forms complex objects within an environment that dark matter has already shaped. This hierarchy suggests that to understand why the universe looks the way it does, it is necessary to understand the properties of dark matter more than the details of luminous matter alone. Small-scale details within this picture reveal further hints and tensions. Some simulations of cold dark matter predict dense central peaks in the distribution of mass within halos, while observations of certain dwarf galaxies suggest flatter cores. The number of small satellite galaxies seen around large galaxies such as the Milky Way appears lower than early dark matter simulations suggested. These discrepancies have inspired refinements in both simulations and interpretations. When the complex effects of ordinary matter are modelled in more detail, including feedback from star formation and explosive events, some of these apparent conflicts lessen. They may indicate that the interplay between dark and ordinary matter is more intricate than first assumed, or that dark matter has additional properties beyond the simplest cold collisionless picture. In either case, they serve as reminders that the invisible scaffolding, while broadly successful in explaining large-scale patterns, still contains unresolved features. Another layer of subtlety arises from the influence of dark energy on structure formation. As dark energy drives the accelerated expansion of the universe, it slows the growth of new structures. Gravity from matter pulls to form clusters and filaments, while dark energy acts as a kind of background influence that stretches space and dilutes the effectiveness of that pull on very large scales. The balance between dark matter and dark energy determines not only how structures form, but also when their growth begins to stall. Measurements of clustering at different cosmic times made by looking at galaxies and quasars at various distances therefore carry information about both components. They show that structure grows rapidly in the early universe when matter dominates, and more slowly in recent times as dark energy becomes more important. The invisible scaffolding of dark matter thus shapes not just the pattern of galaxies, but also the timeline of their assembly under the influence of a still more mysterious dark energy that sets the overall pace of cosmic expansion. Together, these layers of evidence present a coherent though incomplete picture. The universe appears to be threaded with dark matter structures that began forming long before the first stars ignited. Ordinary matter falls into these structures, cools, and gives rise to galaxies whose distribution traces the underlying mass. The resulting cosmic web is detected indirectly through galaxy positions, clustering statistics, and the weak bending of light, all of which point toward a dominant unseen mass component. Yet the precise nature of that component remains unknown, and small deviations between model predictions and observations hint at deeper physics still to be uncovered. The scaffolding is real enough to map and simulate, but its substance continues to evade direct identification, leaving a central question open at the heart of cosmic structure. What exactly forms the backbone on which the visible universe is built? In a universe ruled by gravity, mass does more than pull on other mass. It also alters the path along which light travels. According to general relativity, the presence of mass and energy curves space-time, and light follows the straightest possible routes within this curved geometry. On human scales, this effect is too small to notice, but on cosmic scales it becomes measurable. When light from a distant galaxy or quasar passes near a massive object, on its way to an observer, its trajectory bends slightly. The result is called gravitational lensing by analogy, with the way a glass lens bends light. Unlike a glass lens, however, a gravitational lens reveals itself not by its own brightness, but by the distortions it imposes on background sources. This makes lensing a direct way to detect mass, whether that mass is luminous or dark. It turns the universe into a wide natural laboratory, where light from remote sources probes the invisible structure lying in between. The most dramatic examples of gravitational lensing occur when a massive galaxy cluster lies almost exactly along the line of sight to a more distant object. In such cases, the cluster's gravity can produce multiple images of the background source arcs or nearly complete rings of light. The geometry and separation of these lensed images encode information about the total mass of the cluster and how it is distributed. When astronomers analyze these strong lensing systems, they often find that the amount of mass required to produce the observed distortions is far larger than the mass accounted for by visible galaxies and hot gas. Even after including all ordinary matter that telescopes can detect across many wavelengths, the total still falls short. The missing mass behaves like an extended, relatively smooth dark matter halo enveloping the cluster. In these systems, dark matter is not inferred only from the motions of galaxies, but from the way it sculpts the paths of light itself. Most of the time, the alignment between background sources and foreground mass is not so precise, and the lensing effect is weaker. Instead of producing multiple images or striking arcs, a foreground structure very slightly stretches and shears the images of many background galaxies just enough to change their apparent shapes by a small fraction. Any individual galaxy remains nearly unchanged, but when thousands or millions of such galaxies are observed across a wide field, small systematic trends in their shapes appear. These trends trace the cumulative effect of what is known as weak gravitational lensing. By statistically analyzing these distortions, astronomers can reconstruct maps of the projected mass distribution in the foreground, effectively weighing regions of the sky, without assuming anything about how much of the matter is dark or luminous. These maps reveal that mass extends well beyond the regions lit by galaxies and hot gas. The outskirts of clusters, the bridges connecting neighboring structures, and even large underdense regions show signatures of an invisible component that follows gravity but not light. One of the most striking applications of gravitational lensing involves systems where two galaxy clusters have collided. In such events, different components of the clusters respond differently to the collision. The stars inside galaxies are relatively sparse, and can pass through one another with few direct interactions, while the diffuse gas that fills the space between galaxies behaves like a fluid. When two clusters merge, their galaxies largely interpenetrate, but their gas clouds collide, slow down, and heat up, emitting X-rays that can be observed by space-based telescopes. Dark matter, if it interacts only weakly with ordinary matter and with itself, except through gravity, should behave more like the stars passing through the collision with little resistance. The bullet cluster. A widely studied example of such a system provides a clear illustration. Observations show two main components: an offset distribution of hot X-ray emitting gas, and a separate distribution of mass inferred from gravitational lensing. The X-ray images reveal whether normal gas has piled up and slowed during the collision, while lensing maps show where most of the mass resides. These two maps do not align. Instead, the peaks of the mass distribution sit closer to the galaxies and away from the densest gas. This separation suggests that the dominant mass component has passed through the collision with minimal interaction, as dark matter would in the simplest models. Ordinary matter in the form of gas has been held back while the invisible mass has continued on its presence, shown only by the way it bends light. Similar behavior appears in other merging cluster systems, each with its own geometry and history. In several cases, mass maps derived from lensing are offset from the bulk of the X-ray emitting gas, again indicating that the main gravitating component does not collide and slow in the same way as ordinary matter. While each system is complex and must be interpreted with care together, they support the idea that most of the mass in clusters is in a form that feels gravity strongly, but interacts only weakly in other ways. These observations place constraints on how often dark matter particles can collide with one another or with normal matter. If dark matter were made of compact objects such as black holes in large numbers, or if it had strong non-gravitational interactions, the patterns in merging clusters would likely look different. The apparent ability of the mass to pass through collisions with little drag fits well with a picture of dark matter as a diffuse, weakly interacting medium. Gravitational lensing also exposes dark matter structures in environments where visible traces are scarce. In very faint or ultra-diffuse galaxies where the starlight is faint and spread out, lensing measurements can reveal high mass-to-light ratios. In some cases, the data indicate that these systems are dominated by dark matter to an even greater degree than typical galaxies, containing only a small sprinkling of stars embedded in massive halos. On larger scales, surveys that combine weak lensing with galaxy distance measurements detect filaments of matter connecting clusters, structures that are faint or invisible in light, but clearly present in the mass maps. These findings reinforce the picture of a universe in which dark matter provides a nearly continuous background in which galaxies are immersed. The ability of gravitational lensing to detect mass without relying on its luminosity makes it a powerful independent test of the dark matter idea. It ties the existence of unseen mass to the bending of space itself, not just to the motions of objects within that space. At the same time, lensing observations introduce new layers of complexity. The reconstruction of mass maps from weak lensing data depends on precise measurements of galaxy shapes, corrections for instrumental effects, and careful statistical analysis. Systematic errors must be controlled to avoid misinterpreting random alignments or image distortions as genuine signals. As surveys grow deeper and wider, the volume of data increases, demanding new methods to extract the subtle patterns imprinted by dark matter. Even with these challenges, the broad result remains robust. Whenever mass is measured by its effect on light rather than by its emitted radiation, the universe consistently appears heavier than ordinary matter alone would suggest. The mismatch is not confined to a single type of system or a narrow range of scales. It extends from individual galaxies to massive clusters and the vast web between them. Lensing confirms in a way that does not depend on how stars shine or how gas emits X-rays that there is more gravitating material than can be seen. In this sense, gravitational lensing marks regions where dark matter is likely to be densest, shaping the images of distant objects through the geometry of space. Through this effect, the invisible becomes partially mapped. The universe starts to yield a direct, though still incomplete, cartography of its unseen mass, pointing again toward the central unresolved question: what is the substance that so confidently bends light while remaining dark to every other probe? Once dark matter is accepted as a major contributor to the mass of the universe, the question shifts from where it is to what it is. The gravitational evidence accumulated from galaxy rotation, cluster dynamics, large-scale structure, and gravitational lensing points strongly to an unseen component, but gravity alone does not specify its nature. The simplest working assumption is that dark matter consists of some kind of particle, or perhaps several kinds, that interact very weakly with ordinary matter and with light. Under this assumption, dark matter is present everywhere, forming halos and filaments, but passes almost unhindered through gas-dust stars and detectors. It builds the backbone of cosmic structure while remaining almost transparent to everything except gravity. This picture leads naturally to the idea of a new massive particle that interacts via a force much weaker than electromagnetism and does not carry electric charge. Such a particle could have been produced in large numbers in the hot early universe, and then cooled and slowed as the universe expanded, becoming the cold dark matter invoked in simulations of structure formation. Candidates of this general type, often described as weakly interacting massive particles, arise in several theoretical extensions of known particle physics. These models predict that dark matter particles might occasionally scatter off atomic nuclei or annihilate with one another, releasing detectable byproducts. If so, extremely sensitive experiments might record a small but unmistakable signal of their presence in carefully shielded detectors. To search for such rare interactions, laboratories construct detectors deep underground beneath mountains or under kilometers of rock to shield them from most background radiation. Inside these facilities, large tanks filled with very pure liquids such as xenon or argon, or solid detectors cooled to very low temperatures, are monitored with exquisite care. The hope is that once in a long while a dark matter particle passing through Earth will collide with a nucleus in the detector, transferring a small amount of energy. This energy might appear as a faint flash of light, as a tiny electrical signal, or as a minute vibration, depending on the detector technology. These experiments must distinguish such possible events from a sea of background signals produced by cosmic rays, natural radioactivity, and instrumental noise. Over the past decades, successive generations of detectors have become larger, cleaner, and more sensitive. They have probed an ever wider range of possible masses and interaction strengths for dark matter particles. From time to time, a particular experiment has reported a hint of an excess above expected background, sparking interest and follow-up investigations. However, when independent experiments with different methods and target materials attempt to confirm these hints, the signals often fail to appear. The overall pattern has been one of non-detection, where no convincing, repeatable signature of dark matter scattering has yet emerged. Each null result is not simply a disappointment, it also provides information. It rules out certain combinations of dark matter mass and interaction strength, narrowing the range of possibilities. The allowed space for a dark matter particle that interacts through simple weak forces with ordinary matter has shrunk considerably. At the same time, the absence of straightforward signals has encouraged consideration of more subtle possibilities. Dark matter might be much lighter or much heavier than originally assumed. It might interact even more weakly than expected, or it might couple to normal matter in ways that are not captured by the simplest models. Another strategy looks not for scattering events in detectors, but for signs that dark matter annihilates or decays in space, producing observable particles. If dark matter particles can annihilate when they meet regions of high density, such as the centers of galaxies or clusters, could produce gamma rays, positrons, or other particles at rates above those expected from known astrophysical processes. Space-based observatories and ground-based telescopes sensitive to high-energy radiation therefore search for unexplained excesses in these channels. Some measurements have hinted at possible anomalies such as a surplus of certain types of cosmic rays, or features in gamma-ray maps near the center of the Milky Way. However, the astrophysical environments involved are complex. Pulsars, supernova remnants, and other energetic sources can mimic or obscure the expected signatures. As with direct detection, intriguing clues have not yet solidified into a clear identification. the sky does not yet display a definite, unambiguous imprint that can be traced back to dark matter interactions with high confidence. A third avenue involves creating dark matter particles in high-energy collisions, in particular at particle accelerators such as the Large Hadron Collider. In these machines, protons are sped up to near the speed of light and smashed together at high energies. The collisions can produce a wide variety of particles, some familiar, some potentially new. If dark matter particles are light enough and carry appropriate interactions, they might be produced in these violent events. Because they would pass through detectors without leaving direct traces, their presence would be inferred from missing energy and momentum in the collision products. Physicists search for events in which visible particles emerge in patterns that suggest something unseen has carried away a portion of the energy. So far, these searches have not found clear evidence of new particles that fit the properties required of dark matter. The theoretical frameworks that once made certain dark matter candidates seem almost inevitable have been constrained by the absence of discoveries. Yet the parameter space is vast and many variants remain viable. Beyond these more traditional candidates, other possibilities populate the theoretical landscape. One idea is that dark matter consists of extremely light particles whose wavelength on galactic scales gives rise to wave-like behavior, smoothing out small-scale structure, and perhaps addressing some apparent tensions between observations and standard cold, dark matter simulations. Another proposal involves axions, hypothetical particles originally introduced to solve a problem in the theory of the strong nuclear force. If they exist in large numbers, axions could form a cold diffuse background that behaves as dark matter. Experiments to detect axions use strong magnetic fields and resonant cavities to try to convert these particles into observable photons scanning through different frequency ranges. So far, no definitive signal has been seen, but the search continues, gradually covering more of the parameter space. Yet another possibility is that dark matter is not a single particle species, but a more complex dark sector, perhaps with its own forces and interactions largely decoupled from ordinary matter. In such a scenario, dark matter might form bound states, radiate dark light, or undergo rich internal dynamics that still lead to the simple, gravitational behavior observed on large scales. This would make the dark sector somewhat analogous to the visible sector, which includes atoms, molecules, and radiation, while remaining mostly invisible to current instruments. Such models are difficult to test directly, but they offer new ways to think about how unseen components might behave. The persistent lack of direct or indirect detection does not invalidate the gravitational evidence for dark matter, but it does deepen the mystery. A component that dominates the mass of the universe continues to elude identification in experiments designed to capture even the faintest trace of its interaction with ordinary matter. Each improved search that finds nothing reinforces the idea that dark matter, if it is composed of particles at all, interacts in ways that are more subtle or more remote from known forces than originally envisioned. It also keeps open the possibility that some assumption in the current approach is incomplete. Perhaps gravity behaves differently under certain conditions, reducing the need for unseen mass. Perhaps dark matter is partly made of compact objects that have not yet been fully accounted for, though many constraints from microlensing and other observations limit this option. Or perhaps the particle nature of dark matter lies in a range of properties that current experiments are not yet configured to explore. In the meantime, dark matter remains defined mainly by three robust properties. It exists in the sense that multiple independent observations require additional gravitating mass. It interacts with gravity in essentially the same way as ordinary matter-shaping orbits and bending light. And there is a great deal of it, far more than all visible stars and gas combined. These basic facts are firmly grounded in observation. The details beyond them, however, remain open. The universe offers strong hints that something massive and invisible pervades space, but it has not yet revealed how that something fits into a wider framework of particles and forces. The search for dark matter thus occupies a particular place in modern science. It is guided by clear evidence and well-defined targets, yet it is continually reshaped by the absence of signals where they are most expected. This tension between what must be present and what refuses to show itself keeps dark matter at the frontier of both astrophysics and particle physics, an unseen component whose ghostly gravitational signature is clear while its microscopic identity stays concealed. In the classical picture of an expanding universe, gravity plays a steady restraining role. Matter pulls on matter, and over long times the mutual attraction of all mass gradually slows the overall expansion. If the universe begins in a hot, dense state and has been expanding ever since then, the rate of that expansion should decrease as time passes, unless something acts in the opposite direction. For much of the 20th century, this expectation guides the way cosmologists think about the fate of the universe. Measurements aim to determine whether the expansion will eventually halt and reverse in a recollapse, or whether it will continue forever, but at a diminishing rate. In either case, gravity is assumed to oppose the expansion, never to accelerate it. The first quantitative step in this story comes when Edwin Hubble and his collaborators measure distances to nearby galaxies and compare them with the shifts in their spectral lines toward longer wavelengths. In 1929, this work reveals a roughly linear relationship between distance and what is now called redshift. The farther a galaxy is, the faster it appears to recede. This relation suggests that space itself is stretching, carrying galaxies apart. For decades afterward, astronomers refined the measurement of this expansion rate, but the central question remains how that rate changes over time. To probe this, it is necessary to look far back to times when the universe is much younger, and compare the expansion then with the expansion now. Doing so requires reliable distance indicators, objects whose intrinsic brightness can be inferred with reasonable confidence. Among the best of these are certain types of stellar explosions known as Type 1 or supernovae. These events occur when a white dwarf star in a binary system accumulates material from its companion until it reaches a critical mass and undergoes a thermonuclear runaway. The resulting explosion releases a large and fairly uniform amount of energy. Because Type 1 or supernovae reach nearly the same peak luminosity, they act as standard candles. By measuring how bright they appear, astronomers can estimate how far away they are. In the late 1980s and early 1990s, teams of astronomers set out to use distant Type 1, a supernovae, to trace the expansion history of the universe. They observe these brief bright events in galaxies billions of light-years away, measure their redshifts, and compare their apparent brightness with what would be expected in different cosmological models. If gravity has been slowing the expansion, then distant supernovae observed as they were in the past should appear brighter than they would in a universe expanding at a constant rate, because they would be closer than in the constant expansion case. The data reveal the opposite trend. Distant supernovae appear systematically fainter than anticipated. They seem to be farther away than they should be if the expansion has been steadily decelerating. After careful checks for dust evolution of supernova properties and other possible systematic effects, the most straightforward interpretation emerges: the expansion of the universe is not slowing down, it is speeding up. At some time in the past few billion years, a transition has occurred from a decelerating to an accelerating phase. This discovery, announced independently by two major collaborations in the late 1990s, introduces a new ingredient into cosmology. To account for the observed acceleration within general relativity, an additional component with negative effective pressure is required, something that acts not as a pull, but as a gentle push on cosmic scales. This component receives the descriptive name dark energy. Its presence changes the balance of the cosmic inventory. Matter, including dark matter, still slows the expansion by mutual attraction, but dark energy drives it to accelerate. The relative strengths of these contributions determine how the expansion rate has changed over time. If dark energy behaves like a constant property of space, its influence grows as the universe expands, eventually surpassing the attractive effect of matter. The supernova observations thus do more than reveal acceleration. They imply that some form of energy associated with empty space must be significant today. Independent lines of evidence soon support this conclusion. The detailed pattern of temperature fluctuations in the cosmic microwave background indicates that the geometry of the universe is very nearly flat on large scales. In a simple model, this flatness requires that the total energy density equals a specific value. However, the amount contributed by matter, both ordinary and dark as inferred from galaxy clusters and large-scale structure, falls short. To satisfy the flatness indicated by the microwave background, a smoothly distributed component is needed to make up the difference. Dark energy, first introduced to explain supernova data, fits this role. Measurements of how galaxies cluster at different epochs, including features known as baryon, acoustic oscillations that act as standard rulers in space, provide additional support. They trace how the expansion rate evolves with time, and their results align with a universe in which dark energy has become dominant in recent cosmic history. Despite this convergence, the physical nature of dark energy remains obscure. One possibility is that it is simply a cosmological constant, a term that Albert Einstein once adds to his equations of general relativity to allow for a static universe, and later sets aside. In modern terms, the cosmological constant corresponds to a constant energy density of the vacuum, a property of space that does not dilute as the universe expands. If dark energy is such a constant, its density stays the same while the density of matter decreases as space grows. Over time, the vacuum energy comes to dominate, leading to persistent acceleration. This simple model matches many current observations when the density of the cosmological constant is chosen appropriately. However, when theoretical physicists attempt to calculate the expected vacuum energy by summing contributions from quantum fields, the result is vastly larger than the observed value by many orders of magnitude. This discrepancy, sometimes called the vacuum catastrophe, is one of the greatest unsolved problems in fundamental physics. It suggests that some major piece of understanding is missing, either in how vacuum energy is computed or in how it gravitates. Another possibility is that dark energy is not strictly constant, but arises from a slowly evolving field that changes over cosmic time. Such models, often grouped under the term quintessence, allow the effective relation between the pressure and density of dark energy to vary. If dark energy evolves, the rate of cosmic acceleration would change in a way that could in principle be tracked by precise observations of expansion at different epochs. Current data are consistent with a constant dark energy within the limits of measurement, but they do not yet exclude modest time variation. Future surveys aim to tighten these constraints by mapping larger volumes of the universe with greater precision. A more radical approach is to question whether general relativity itself holds exactly on the larger scales. Perhaps the observed acceleration is not due to a new form of energy, but rather to a modification of gravity at very low densities or over immense distances. Various alternative theories have been proposed in which the gravitational force law changes beyond a certain scale, or in which additional geometric terms appear in the equations that mimic the effect of dark energy. These models must not only reproduce the supernova data, but also remain consistent with the precise tests of gravity in the solar system and with the structure of the cosmic microwave background. Many such theories face difficulties matching the full range of observations, but the exploration underscores that dark energy could be a sign that the current understanding of gravity is incomplete. On smaller scales, the influence of dark energy is negligible. Within galaxies, galaxy clusters, and even groups of clusters, the gravitational pull of matter dominates. Bound systems remain intact, and their internal dynamics are governed almost entirely by the attraction of mass. Dark energy becomes important only on scales close to the overall size of the observable universe, where the cumulative effect of vacuum-like energy shapes the global expansion. In this sense, dark energy is a background influence quietly altering the large-scale behavior of space while leaving local structures largely unaffected. Its presence is inferred not from local experiments, but from the way distant light and large-scale structures encode the history of expansion. The introduction of dark energy completes in a provisional way the picture of a universe composed mainly of dark components. Dark matter provides the scaffolding on which galaxies and clusters form, while dark energy governs the ultimate pace of expansion. Together they account for the vast majority of the cosmic energy budget, yet both are known primarily through their gravitational effects and through the patterns they imprint on light from distant objects. Their microscopic origin is unknown. The same observations that make the current cosmological model successful also emphasize its provisional nature. The accelerating universe revealed by supernovae and confirmed by multiple probes is a real phenomenon, but the agent behind it remains unidentified. The data describe what dark energy does. It causes space to expand faster over time and contributes a smooth energy density that does not clump on small scales. They do not yet reveal what dark energy is, why its density has the value it does, or whether it will remain constant forever. These open questions turn the discovery of cosmic acceleration from a tidy conclusion into a starting point for a deeper inquiry, one in which the large-scale behavior of the universe points toward gaps in the understanding of both matter and gravity. The idea that dark energy might be a property of empty space leads directly to a closer look at what empty space is. In everyday terms, a vacuum is the absence of matter and radiation, a region cleared of particles and fields. In modern physics, this simple picture does not hold. Quantum field theory describes even the lowest energy state of a field as containing fluctuations, small variations that cannot be removed. These zero-point fluctuations arise from the basic rules of quantum mechanics, which do not allow both the value of a field and its rate of change to be fixed precisely at the same time. As a result, even in its ground state, a field carries a residual energy. Summed over all fields and all possible wavelengths, this energy is sometimes described as vacuum energy. If dark energy is simply this vacuum energy acting through gravity, then its density corresponds to the energy density of the quantum vacuum. Observations of cosmic acceleration together with measurements of the cosmic microwave background and large-scale structure indicate that the dark energy density is small on everyday scales, but significant on cosmological ones. When expressed in common laboratory units, it is extremely low, yet its cumulative effect across the vast volume of the observable universe is substantial. The difficulty arises when theoretical estimates of vacuum energy are compared with this observed value. In simple calculations, contributions from quantum fields at high frequencies add up to an energy density that is many orders of magnitude larger than the inferred dark energy density, perhaps by factors as large as 10 raised to the power of 60 or more depending on the cutoff scale used. This mismatch is so extreme that it suggests not just a numerical discrepancy, but a fundamental gap in understanding. If the naive calculation were correct, the universe would either have expanded so rapidly that structures could never form, or would have behaved in ways completely unlike what is observed. One response is to suppose that different contributions to vacuum energy nearly cancel. Positive and negative terms arising from various fields or symmetries might balance one another so closely that only a tiny residual remains, which then appears as dark energy. However, achieving such a delicate cancellation without a clear underlying principle is challenging. Known symmetries such as supersymmetry can reduce vacuum energy, but to match observations they must be broken in specific ways, and the resulting residual still tends to be too large. The degree of fine-tuning required in which large quantities, almost but not exactly cancel to produce a small remainder, strikes many physicists as unsatisfactory. It shifts the puzzle rather than resolving it, raising the question of why the cancellation is so precise. Another idea is that what is computed in simple quantum field theory is not directly the quantity that gravitates. Perhaps some mechanism in a more complete theory of gravity, possibly involving quantum aspects of spacetime itself, modifies how vacuum energy couples to the geometry of the universe. In such a scenario, the enormous raw vacuum energy might be real in some sense, but does not act on the expansion in the expected way. Instead, only a small effective portion influences cosmic acceleration. Since a fully developed theory of quantum gravity is not yet available, this remains speculative. It illustrates how dark energy connects not only to cosmological observations, but also to deep questions about the union of quantum physics and gravity. Observationally, dark energy appears smooth and nearly uniform. Unlike matter, it does not clump into galaxies or clusters. Its density seems roughly the same in all directions and at all locations, at least within current measurement limits. This uniformity fits naturally with the idea of vacuum energy, which would be the same everywhere. It is described by an effective relation between pressure and density, often parameterized by a quantity that compares them. For a pure cosmological constant, this relation has a fixed value of -1. Present data from supernovae, the cosmic microwave background galaxy clustering and weak gravitational lensing are consistent with such a constant value. They do not, however, yet rule out modest deviations. This leaves room for models in which dark energy is not absolutely constant, but evolves slowly over time. In these models, sometimes grouped under the term quintessence, dark energy arises from a scalar field that rolls slowly down a potential energy curve. The field's energy density and pressure change as it evolves, leading to a time-dependent contribution to the expansion. In some cases, dark energy density may have been less important in the early universe and grown relative to matter only in recent epochs, helping to explain why cosmic acceleration becomes significant only after billions of years. In others, dark energy might gradually dilute or transform, leading to a future different from that predicted by a strict cosmological constant. Quintessence fields can also allow the effective pressure-density relation to differ slightly from -1, either being somewhat greater or somewhat less. If it is greater than -1, dark energy still accelerates the expansion, but does so in a way that might diminish in the far future. If it is less than -1, the acceleration can become stronger over time, potentially leading to more extreme outcomes. Observational programs aim to measure this relation and its possible evolution, with increasing precision seeking subtle signatures that could distinguish between a constant vacuum energy and a dynamic field. The data so far favor a value close to -1 with little variation, but the uncertainties leave room for gentle departures. Another set of proposals treats dark energy as emerging from collective effects of inhomogeneities, such as the influence of large-scale structure on the average expansion. In this view, the standard cosmological description which treats the universe as perfectly smooth on large scales may miss back reaction effects from its clumpy nature. Under certain conditions, these effects might mimic an accelerated expansion without a new energy component. Detailed analysis suggests that the magnitude of such back reaction in realistic models is small, but the possibility that averaging over a complex geometry could alter the apparent behavior of expansion illustrates how the interpretation of observations depends on the theoretical framework used. Quantum fluctuations themselves provide another angle. In a simple picture, empty space is filled with temporary excitations, brief appearances of particle and antiparticle pairs that form and vanish rapidly. Phenomena such as the Casimir effect, in which two closely spaced conducting plates experience a small attractive force, demonstrate that vacuum fluctuations can have measurable consequences in certain configurations. It is tempting to connect these fluctuations directly to cosmic dark energy, viewing the acceleration of the universe as a large-scale manifestation of a restless quantum vacuum. However, when the same theoretical tools are applied to estimate the vacuum energy that would drive cosmic acceleration, the resulting overestimate returns. The Casimir effect depends on changes in vacuum energy between different configurations, not on its absolute value. This distinction complicates simple analogies between laboratory vacuum effects and cosmological dark energy. Beyond specific models, the presence of dark energy raises a collection of related questions. Why does its density have the value it does, neither enormous nor strictly zero? Why has it become important only in the recent fraction of cosmic history, roughly when galaxies, stars, and planets have had time to form? In a universe that has expanded and diluted for billions of years, it is notable that the densities of matter and dark energy are of the same order of magnitude today, even though they evolve differently with expansion. Some approaches invoke a selection effect, suggesting that observers are more likely to arise in epochs when structure can form and persist, which constrains the possible values of dark energy. Others search for dynamical explanations that link the onset of acceleration to processes in fundamental physics. None of these ideas has yet achieved a status comparable to that of established physical laws, but they serve to illustrate how deeply the problem of dark energy reaches into both cosmology and theoretical physics. As measurements improve maps of galaxies' clusters and lensing patterns across larger and deeper volumes of space, will refine the history of cosmic expansion. Experiments designed to track how the clustering of matter evolves and how light from distant sources is stretched over time will test whether dark energy behaves exactly like a cosmological constant or shows hints of variation. If deviations are found, they may point toward dynamic fields or modified gravity. If none are found and the behavior remains consistent with simple constant vacuum energy, the puzzle will become sharper in a different way. A very small but non-zero cosmological constant will stand as an unambiguous feature of the universe that demands a theoretical explanation yet continues to resist one. In either case, the vacuum of space, once thought of as simple emptiness, remains a central player in the story of cosmic evolution, carrying an energy that shapes the largest structures and the ultimate trajectory of the universe, while revealing only limited aspects of its origin or nature. Once dark energy is taken seriously as a genuine component of the universe, its behavior over time becomes more than a technical detail. It becomes the scriptwriter for the long-term future of cosmic history. The same unseen influence that now accelerates the expansion will, if it persists, determine how galaxies, stars, and larger structures evolve on timescales far beyond the current age of the universe. The starting point for this discussion is the way different components of the cosmos respond to expansion. Ordinary matter, whether in stars, gas, or dark matter, halos becomes more dilute as space grows. The density of such matter decreases as more volume is created between objects, even though the total amount of matter stays the same. Radiation such as light thins even faster, because its energy is also stretched to longer wavelengths as space expands. In contrast, if dark energy behaves like a true cosmological constant, its density remains essentially unchanged as the universe grows. Every region of space, no matter how large the whole becomes, carries the same average amount of this vacuum-like energy. As time passes, matter becomes less important relative to dark energy. The balance shifts so that the expansion is increasingly governed by the properties of dark energy alone. In the simplest constant density case, the universe asymptotically approaches a state in which galaxies that are not gravitationally bound to one another recede at ever-increasing relative speeds. Beyond some distance, the expansion becomes so rapid that light emitted now from one region may never reach another. Structures that are already held together, such as galaxies and galaxy clusters, remain intact, but the space between these islands stretches. Over an immense span of time, the observable universe of any given galaxy becomes more and more empty as distant systems slip beyond the horizon, defined by the speed of light and the accelerating expansion. The night sky gradually loses its external galaxies, leaving only the local group or its remnants as visible structures. This outcome is sometimes described as a slow thinning or cooling of cosmic activity, in which star formation declines. Existing stars burn out, and energy sources become more sparse, while dark energy continues to dominate the background. If dark energy is truly constant, this gradual fading and isolation is the long-term trend. The universe does not recollapse, but continues to expand with structure on the largest scales effectively frozen and local systems persisting as long as their internal energy sources allow. This scenario is not catastrophic in any sudden way. It is a quiet evolution in which distance and emptiness steadily increase. The situation becomes more complex if dark energy is not strictly constant. If its behavior is described by an effective relation between pressure and density that differs even slightly from that of a pure cosmological constant, the long-term prospects change. When this relation is such that dark energy's influence weakens over time, perhaps because it arises from a field that slowly rolls toward a state with lower energy, the current acceleration might be a temporary phase. In some models of this type, dark energy density gradually decreases faster than the density of matter, allowing matter once again to dominate in the distant future. If that occurs, the expansion could slow and eventually behave more like a matter-dominated universe, in which the growth of new structure might resume in some form, or at least the acceleration would diminish. In more extreme versions, dark energy might even change sign, effectively acting like a negative contribution to the energy budget and leading to a future collapse. Such possibilities remain speculative and are constrained by present observations which do not show strong evidence for large time variation. Still, they are allowed within current uncertainties and illustrate how sensitive the cosmic outcome is to the microphysics of dark energy. An opposite class of models arises when the effective pressure of dark energy is even more negative than in the cosmological constant case. In these phantom scenarios, the energy density of dark energy increases as the universe expands. Instead of being diluted, this component grows stronger with time driving acceleration that becomes ever more rapid. If such behavior persists, the expansion rate eventually becomes so extreme that not only distant galaxies but even bound systems are affected. In a far future version of this trajectory, galaxy clusters would be torn apart by the accelerating expansion, followed by the disruption of galaxies themselves, and much later of planetary systems and smaller structures. In the most dramatic form of this idea, sometimes called a RIP scenario, the scale factor of the universe grows without bound in a finite amount of time, and all bound structures are ultimately pulled apart. Although this is an internally consistent possibility, within some models of dark energy current data do not require such behavior. They are compatible with an effective pressure-density relation close to that of a simple cosmological constant. Nevertheless, the existence of such models underscores that small differences in the fundamental properties of dark energy can lead to very different long-term outcomes. The question of which trajectory the universe follows is in principle accessible to observation. By measuring how the expansion rate changes with redshift, how distance indicators behave at various epochs, and how structure growth is affected over time, cosmologists can infer the effective behavior of dark energy. If it is constant, the relation between pressure and density has a fixed value, and the expansion history follows a specific curve. If dark energy evolves even slowly, the curve changes. High-precision data from supernovae baryon, acoustic oscillations, weak lensing, and other probes are therefore not only measurements of current conditions, but also glimpses into the long-term script. At present, the combined evidence points to an expansion history that is consistent with a cosmological constant within the errors. The effective relation between pressure and density appears close to the characteristic value for vacuum energy, and any time variation is limited. This suggests that the universe may indeed be heading toward a state of continued acceleration, with gradually thinning matter. But the uncertainties are still large enough to leave room for more complex behavior. A slight deviation from a constant could be hiding within the measurement noise waiting to be revealed by more sensitive observations. There is also the possibility that the concepts used to describe the future, such as constant dark energy and simple matter dilution, are approximations that will give way to a more unified description once the true nature of dark energy and its relation to gravity is better understood. In describing cosmic futures, it is important to note that these scenarios operate on timescales vastly longer than the current age of the universe. Even in the constant dark energy case, the isolation of galaxies and the fading of the night sky, as distant structures cross causal boundaries, would unfold over periods so extended that they are effectively beyond direct experiment. They are projections grounded in current laws of physics applied over many orders of magnitude in time. As with any extrapolation, their reliability depends on those laws remaining valid, and on the absence of new physics that becomes relevant at late times. Since dark energy already marks a domain where understanding is incomplete, the long-term extrapolation into the far future is inherently tentative. Even so, thinking through these possibilities highlights how a single parameter, the behavior of dark energy, ties together present data and eventual fate. Whether the universe experiences an endless, gently accelerating expansion, a more complicated sequence in which acceleration turns off or reverses, or an extreme amplification of expansion, depends on properties that are currently inferred only indirectly. Events that occur billions or trillions of years from now are encoded in subtle ways in the patterns of light arriving today from distant galaxies and the structure of the cosmic microwave background. The fact that the same observations used to infer the present composition of the cosmos also carry implications for its ultimate trajectory underscores the central role of dark energy in any comprehensive picture. It is not merely another component in the inventory, but the defining influence on the larger scale behavior of space-time. At the same time, the wide range of possible futures allowed by small uncertainties in its properties serves as a reminder that the story is not yet complete. The universe could be heading toward a quiet, elongated era of gradual isolation, or toward a more complex sequence shaped by dynamics that have not yet been revealed. The line between these outcomes is drawn by a component of reality that for now is known more by its global effect than by any direct local signature. As the picture of a universe dominated by dark matter and dark energy becomes more widely used, attention shifts from establishing this framework to testing its limits. The current standard model of cosmology, which combines cold, dark matter with a cosmological constant, successfully explains a broad range of phenomena: the pattern of temperature variations in the cosmic microwave background, the large-scale distribution of galaxies, the statistics of gravitational lensing, and the overall expansion history as inferred from many distance and scale measurements. Yet as data grow more precise and diverse, certain tensions and anomalies begin to appear at the edges of this success. These features do not overturn the model, but they suggest that it may be an approximation accurate in many regimes, yet incomplete in ways that careful observation can detect. One of the most discussed tensions arises in measurements of the current expansion rate of the universe, often summarized by a parameter that describes how fast distant galaxies recede with distance. When this rate is inferred from the cosmic microwave background using the standard cosmological model to project from the early universe to the present, one value is obtained. When it is measured more directly in the nearby universe, using distance ladders, based on pulsating stars type 1, a supernovae and other standard candles, a higher value emerges. Over time, as both methods improve, the discrepancy persists, and in some analyses grows more statistically significant. The early universe measurements, which rely on fitting the microwave background, with a model that includes dark matter and dark energy, suggest a slower present expansion than the late universe distance measurements indicate. This mismatch, known informally as a tension in the expansion rate, lies at the interface between different ways of probing the cosmos. It could signal unrecognized systematic effects in one or both sets of measurements, such as subtle biases in distance calibration or complexities in the interpretation of the microwave background. Alternatively, it could hint that the standard model, while largely correct, is missing an ingredient that alters the connection between early and late universe observables. Changes in dark energy behavior over time, extra-relativistic particles in the early universe, or modifications to gravity that become important at particular epochs have all been considered as possible resolutions. None has yet provided a universally accepted solution, but the continued presence of the tension acts as a pressure point, encouraging refinements in both observations and theory. On smaller scales in the realm of galaxies and their satellites, other discrepancies appear. Simulations of cold, collisionless dark matter predict a rich population of small dark matter halos orbiting larger galaxies like the Milky Way. These halos are potential hosts for dwarf galaxies, faint systems with few stars but dominated by dark matter. Early comparisons between simulations and observations suggest that the number of visible satellite galaxies is lower than expected, and that the inner density profiles of some dwarfs are flatter than the steep central peaks predicted by simple models. These issues are sometimes summarized as problems of missing satellites and core cusp differences. Over time, deeper surveys reveal more faint satellites and more sophisticated simulations that include the effects of gas star formation and energetic feedback show that ordinary matter can reshape the inner structure of dark matter, halos softening cusps into cores. This progress eases some of the early tensions, suggesting that once the full interplay between baryonic processes and dark matter is taken into account, the discrepancies diminish. Still, questions remain about the detailed match between specific galaxies and the simplest dark matter expectations. Some ultra-diffuse systems seem to have far less dark matter than anticipated, while others appear to be almost entirely dark matter with minimal starlight. These outliers invite closer study, as they may reveal either rare outcomes of standard processes or hints of new properties in the dark sector. A related set of puzzles concerns regularities in galactic dynamics that are not immediately obvious products of complex formation histories. Relationships between the visible mass of galaxies and their rotation curves, for example, can be summarized in empirical scaling laws that seem surprisingly tight, given the variety of environments and assembly paths. In some formulations, the acceleration at which dark matter effects become pronounced has a characteristic scale appearing in many systems with relatively little scatter. Modified gravity theories, which adjust the laws of motion at low accelerations, naturally produce such regularities, and this has been cited as an argument in their favor. In contrast, standard dark matter frameworks must show how the combination of halo properties, baryonic feedback, and evolutionary pathways conspire to generate these patterns. Simulations are increasingly able to reproduce many of the observed relations, but the degree to which the underlying explanation is generic or finely tuned remains an active area of investigation. These questions do not negate the need for dark matter, which remains strongly supported by gravitational lensing and large-scale structure, but they highlight areas where the simple idea of collisionless cold particles may require refinement. Beyond individual anomalies, there is a broader question about the internal consistency of the standard cosmological model as measurements become more precise. Different ways of estimating the amount of matter and the strength of clustering, for example, from weak lensing surveys and galaxy clustering statistics, can give slightly different answers. In some studies, the amplitude of matter clustering inferred from lensing is a bit lower than what would be expected from microwave background normalized models, leading to another tension in parameters related to structure growth. Once again, this may be due to subtle systematics in measurements or to incomplete modeling of astrophysical effects, but it also opens the door to possibilities such as a small departure from constant dark energy or interactions within the dark sector that suppress growth on certain scales. In this context, dark energy itself is not exempt from scrutiny. While a cosmological constant provides an excellent fit to current data, the door remains open for time variation that is too gentle to have been detected so far. If the effective relation between pressure and density differs slightly from the constant value or evolves slowly, the impact on expansion and structure growth could be small, yet accumulate over cosmic time. In such cases, the standard model would be an approximation valid to current precision, but hiding subtle dynamics. Upcoming surveys that map larger volumes of the universe with more sensitive instruments aim to detect or constrain such deviations, turning small discrepancies in parameters into potential clues about new physics. Some researchers explore more radical options in which both dark matter and dark energy are aspects of a single underlying field or phenomenon, sometimes dubbed unified dark sector models. In these scenarios, what appears as separate components in the standard approach may be different phases or behaviors of a deeper entity. Others investigate modified gravity theories, in which the equations that govern space-time are altered at large distances, producing effects that resemble dark energy without introducing a separate substance. Each of these ideas must pass a high bar. They must reproduce the successes of the standard model across many independent datasets, while explaining the emerging anomalies in a natural way. So far, no alternative has clearly surpassed the cold dark matter, plus cosmological constant framework in overall performance, but the very act of testing them expands the range of possibilities for how cosmic acceleration and unseen mass might arise. In practice, the current situation is one of tension rather than contradiction. The standard model remains a powerful and efficient way to describe the universe, yet it contains seams where measurements and predictions do not align perfectly. These seams cluster around specific questions: why the present expansion rate measured locally differs from that inferred from the early universe, why small-scale structures arrange themselves as they do, and whether matter clustering and lensing parameters are slightly offset. The answers may lie in improved calibration, better control of observational biases, and more realistic simulations. Or they may require the introduction of new ingredients such as interactions in the dark sector, extra light particles, or slowly evolving fields. The universe, having yielded a coherent but dark-dominated picture, now presents these subtle discrepancies as invitations to look more closely. Each small mismatch becomes a potential window into physics beyond the simplest models, a reminder that agreement at the level of broad patterns does not guarantee completeness. The same observations that solidify the case for dark matter and dark energy also hint that their precise roles and origins are not fully captured by their current simple descriptions. In this sense, the apparent cracks at the edges of the model are less signs of failure than of unfinished understanding, indicating that even in a universe now mapped and modelled in remarkable detail, key aspects of its unseen contents may still be awaiting a deeper explanation. In the early decades of the 21st century, the study of dark matter and dark energy enters a phase in which the main outlines of the cosmic inventory are known, but the details of its unseen contents remain elusive. The emphasis shifts toward building instruments and surveys capable of mapping the invisible components with far greater precision and of catching rare phenomena that might reveal their underlying nature. Large ground-based telescopes, wide-field imaging surveys, space missions dedicated to weak gravitational lensing and supernova measurements, and deep underground detectors are all parts of a coordinated effort to transform broad inferences into detailed constraints. Each new project is designed with specific questions in mind. How exactly does structure grow over time? How does the expansion rate evolve across different epochs? How is mass distributed on scales ranging from dwarf galaxies to the cosmic web? And are there any subtle departures from the patterns expected if dark matter is cold and collisionless, and dark energy is a simple cosmological constant? One major line of advance comes from ever more comprehensive maps of the large-scale structure of the universe. Sky surveys that catalogue the positions and redshifts of millions or billions of galaxies provide a three-dimensional picture of how matter is arranged over vast distances. When combined with measurements of weak gravitational lensing, these surveys do more than track light. They trace the underlying mass, including dark matter. By examining how the clustering of galaxies and the lensing signal change with redshift cosmologists, can reconstruct the growth history of structure and compare it with predictions from different models of dark matter and dark energy. Slight deviations from the expected pattern can signal new physics, whether in the form of evolving dark energy interactions in the dark sector or modifications to gravity on large scales. Projects of this kind require stable wide-field imaging, over many years precise calibration, and careful control of systematics, since the distortions imprinted by weak lensing are subtle and easily overwhelmed by instrumental effects. They also demand extensive computational resources both to reduce the data and to simulate many possible universes against which the real one can be compared. Space-based observatories add another dimension by operating above the atmosphere, where they avoid some of the distortions and noise that affect ground-based measurements. Dedicated missions developed by agencies such as NASA and European Space Agency aim to measure cosmic acceleration through multiple techniques at once: detailed supernova light curves, precise weak lensing surveys, and accurate baryon acoustic oscillation measurements. By combining these methods, they can cross-check results and reduce the chance that an unrecognized systematic bias in one technique will mimic or conceal the effects of dark energy. The same missions can also refine estimates of how much dark matter is present, and how it clusters tightening constraints on its properties without directly detecting its particles. Ground-based observatories operated by organizations such as European Southern Observatory complement these efforts with deep spectroscopic surveys that capture the motions and distances of galaxies and quasars across large volumes, adding velocity information to the maps of structure. On smaller scales, focused observations of individual systems continue to play an important role. Detailed studies of dwarf galaxies, satellite systems, and low-surface brightness galaxies probe regimes where dark matter may dominate even more strongly than in large spirals. Precise measurements of their rotation curves, stellar motions, and lensing signatures test how dark matter behaves in environments with shallow gravitational potentials and low baryonic content. any systematic pattern that cannot be reconciled with cold, collisionless dark matter could point to new physics such as self-interactions in the dark sector or wave-like behavior from ultralight particles. Merging clusters of galaxies remain natural laboratories for constraining how collisional or collisionless dark matter is, as new examples are discovered and observed across multiple wavelengths. In parallel, high-resolution simulations that include both dark and ordinary matter strive to mimic these systems in detail, allowing direct comparison between simulated and observed galaxies and clusters. Agreement strengthens confidence in the underlying model, while discrepancies highlight where assumptions about feedback star formation or dark matter properties may need revision. Direct and indirect detection experiments also move into new territory. Underground detectors grow in size and sensitivity, pushing down the limits on how often dark matter particles could scatter off nuclei. Novel materials and detection methods are explored to reach very low mass ranges and extremely weak couplings. Experiments that search for axion-like particles scan more frequencies with higher quality factors using strong magnetic fields and resonant cavities, or new concepts such as dielectric haloscopes. Gamma-ray telescopes, neutrino observatories and cosmic ray detectors monitor the sky for excesses or spectral features that could indicate dark matter annihilation or decay in regions of high density. While each successive round of experiments that finds no signal narrows the parameter space for specific candidates, it also sharpens the questions. If dark matter is a particle wherein mass and interaction, strength can it still hide? If it is part of a more complex dark sector, what signatures might that produce, and are current experiments optimized to see them? The study of dark energy likewise benefits from multiple complementary approaches. Besides supernovae and baryon, acoustic oscillations, measurements of redshift space, distortions in galaxy clustering reveal how the growth rate of structure responds to the balance between matter and dark energy. Weak lensing tomography, in which lensing signals are analyzed in separate redshift slices, provides a time-resolved picture of how mass fluctuations evolve. Cross-correlations between galaxy surveys, lensing maps, and the cosmic microwave background help isolate subtle effects such as the integrated Sachs-Wolf signal, in which photons gain or lose energy as they traverse evolving gravitational potentials in a universe with dark energy. Together, these tests probe whether dark energy behaves exactly like a cosmological constant, or whether there are hints of evolution or deviations from general relativity. Even small departures, if detected robustly, would have profound implications for theories of fundamental physics. As the data become richer, the challenge increasingly lies in interpretation. The standard cosmological model provides a compact description in terms of a handful of parameters, but the underlying physics of dark components is not captured by these numbers. Large collaborations of scientists using sophisticated statistical tools and machine learning techniques work to extract as much information as possible from the observations, while avoiding overfitting and hidden biases. Simulations must incorporate both gravity and complex astrophysical processes to connect theoretical models with what telescopes actually see. At the same time, theorists explore a wide range of possibilities, from subtle interactions in the dark sector to unified models that link dark matter, dark energy, and inflationary dynamics. The interplay between observation, simulation, and theory becomes essential. No single line of evidence is likely to reveal the full truth in isolation. Instead, progress depends on how well different strands of data converge or fail to converge. All of this activity is carried out by a technological civilization that on cosmic scales occupies a very modest niche. A species on a small planet around an ordinary star in a typical galaxy uses sensitive detectors and carefully engineered spacecraft to infer properties of components it cannot see or touch directly. photons that have travelled for billions of years, stretched by cosmic expansion, arrive at detectors and are turned into numbers. Subtle variations in those numbers once processed and compared with theoretical predictions point toward the presence of dark matter, halos the influence of dark energy and possible departures from simple models. In this way, the universe itself becomes the laboratory, and time becomes a tool since light from different distances samples different epochs. The current understanding of dark matter and dark energy is therefore a snapshot in an ongoing process. It rests on a foundation of strong evidence that most of the matter in the cosmos is dark, and that the expansion is accelerating under the influence of a smooth energy component. It also contains acknowledged gaps, the microscopic identity of dark matter, the origin and nature of dark energy, and the reason their densities take the values they do. Future observations and experiments may reveal that dark matter consists of one or more new particles, or that it has richer dynamics than simple collisionless behavior suggests. They may show that dark energy is a true cosmological constant, an unchanging property of space-time, or that it evolves slowly, perhaps linked to fields or symmetries not yet understood. They may even uncover inconsistencies that signal the need for a new description of gravity itself on the larger scales. Whatever the outcome, the universe will retain its role as a guide, constraining which stories about its unseen contents can be true. In this sense, the dark components of the universe act as both a challenge and an invitation. They challenge existing theories by occupying most of the cosmic budget while remaining outside direct detection. They invite new ideas by offering clear quantitative targets against which theories can be tested. The same darkness that makes them invisible in ordinary images ensures that their presence must be inferred through careful cumulative reasoning. As instruments become more sensitive and surveys more extensive, the maps of the invisible 95% of the universe will grow more detailed. The broad outlines may remain or unexpected features may emerge. Either way, the attempt to understand dark matter and dark energy keeps drawing attention back to a simple fact. The familiar world of stars, gas and planets is only a small subset of what exists. The rest continues to shape the universe quietly, leaving patterns in light and structure that a small curious species can with effort decipher, even as the underlying nature of that darkness remains an open question. In the present cosmos, most of what exists does not shine. Galaxies rotate within halos that cannot be seen. Light from distant sources bends around clumps of mass that emit little or no radiation, and the overall expansion of space accelerates under the influence of an energy that appears smooth and uniform. Dark matter and dark energy are introduced to describe these phenomena in a consistent way, and they succeed at linking many observations into a coherent framework. Yet they remain defined mainly by what they do rather than by what they are. Dark matter holds structures together and seeds the cosmic web, but its particle nature or deeper origin is unknown. Dark energy drives acceleration and shapes the long-term behavior of expansion, but its connection to vacuum energy fields or modified gravity is not settled. Observatories on Earth and in space underground detectors and careful analyses of ancient light all contribute pieces to this picture. Each new survey refines maps of mass and expansion. Each null result in a detector narrows the range of possible dark matter properties, and each improved measurement of distance and redshift tightens constraints on dark energy. The universe responds with patterns that are often clear and sometimes puzzling regularities in rotation curves, tensions in inferred expansion rates, subtle deviations in clustering. These features do not yet overthrow the prevailing model, but suggest that it is a step along a path rather than a final answer. In this situation, a technological species on a small world participates in a large-scale process of inference. It collects photons that have crossed enormous distances, measures their energies and directions, and reconstructs the history and contents of the universe from faint signals. The same data that reveal familiar structures also point beyond them, indicating that most of the mass and energy reside in forms not yet directly identified. The darkness in this context is not simply absence, but an active component of the story, guiding the formation of galaxies, setting the pace of cosmic time and defining possible futures. The questions that remain are straightforward to state and difficult to answer. What is the invisible matter that shapes gravity on all large scales? What is the smooth energy that accelerates expansion? And how do these components fit into a broader understanding of physics? As instruments improve and theories evolve, the answers may change, but the underlying situation persists. The visible universe is only a small part of what exists, and the larger unseen portion continues to leave its mark in ways that can be measured, modelled, and slowly understood, even as its full nature remains open.